Good day, everybody. My name is TJ Willits with Veolia Water Technologies, and I'll be the moderator for today's event. I'm just looking at the login for this broadcast here. It looks like there's a lot of people still filtering in. So we're going to give it another minute or two before we start the broadcast. So just bear with us for a few moments, let these people log in, and we'll start just momentarily. Thank you for your patience. And for those that have maybe just signed on there, we're going to wait another minute or two to allow some of the other people that are logging in to join the broadcast at the start here. So thank you for your patience. Okay, we're going to get started with today's presentation. I'd like to welcome everyone to 2 things you should know about grit removal. Just some technical slides that we have here. Obviously, you should be hearing me speak now. Anytime throughout the broadcast, if you're having some audio issues, there are 2 methods to listen to today's audio. You could either listen it through your speakers or your computer audio. If you're having issues with that, we also supply a teleconference number, so you could just switch over on the right side of your screen to phone call, and you'll get some call-in information if you need to try that method to listen to today's presentation. Everyone's microphone is automatically muted since there's so many people attending this broadcast, but we still want to make sure and put an emphasis that it is an interactive event, an interactive webinar. In regards to being an interactive webinar, on the right side of your screen, you should see a question panel or a box, or something like a chat box. Feel free to enter questions throughout today's presentation in that box, and we'll try to get to as many of those as possible after today's main presentation with our expert panelists. And for many of you may already know this, but today's presentation is one of several that are scheduled for the month of May. If you head over to our website, veoliawatertech.com, you could go ahead and find the webinar button link on the homepage, and you could browse some of those other webinars that we have scheduled over the upcoming weeks there and register for those. And we have several webinars offered both in English and in French. In addition to the upcoming webinars that I just mentioned, we also released our library of 40+ webinars that you could watch on demand at your leisure 24/7. And again, those are at our website, veoliawatertech.com. We're going to provide a participation certificate for everyone who's here on the live presentation. To receive that certificate, you don't have to do anything. What will happen is a day or so after the broadcast, you'll be emailed a PDF of your certificate, and that's what it looks a little bit like there on the right-hand side of the screen. And something that's a little bit fun, we are trying to encourage everyone to take the survey after today's broadcast. It really helps us to improve the content that we present here, and also gives us some ideas of potential future webinar topics that we could share with everyone. The fun part is if that you take that survey after the webinar, we're going to enter all the people that fill that out into a raffle to win a $25 gift card, and you'll be notified a day or so after the webinar if you are the lucky winner. And just a little bit about Veolia Water Technologies if you are not familiar with our company. We are the world's leading water and wastewater treatment company. We focus in 3 areas in terms of the types of things that we do. We are leaders in technologies that treat water and wastewater. We assemble those technologies together for projects that meet the specific needs of our clients. And then we, of course, offer a wide range of related services to our clients as well. And now for today's presentation, we are fortunate to have two expert panelists with us. The first panelist that you'll hear from today is Chris Howarth. Chris is a registered PE with over 20 years experience in water and wastewater treatment. And he's worked for both private and public sector organizations in Europe and Canada. And he's currently responsible for municipal business development in Western Canada. Then also with us today is Aurélien Poulet, and he is based in our Montreal office as the Veolia Equipment Application and Tender Team Supervisor. And he has over 20 years of experience in mechanical engineering and 14 years of experience in municipal wastewater treatment. So at this time, I'm going to pass the webinar over to Chris. Chris, are you here with us today?
Yes, I am, TJ. Do you hear me?
Very well. Thank you, Chris.
Great. Thank you. So thank you, everybody, for attending the presentation today. We do have a lot of people on the line, so we're going to be keeping it fairly high level. Hopefully now you can see the agenda on your screens, and hopefully you've already had a chance to look at this, so I'm not going to go through it all line by line. But because we do have a lot of people on the system today, we've decided to keep it pretty high level, kind of like a lunch and learn. And if you want to go into more technical detail or details on things, then that's what the questions are there for. So do please feel free to raise questions whenever you have them, and we'll get to those at the end. You're going to be hearing mostly from me today. Aurélien is available to answer the more difficult questions. He's more of a detailed expert than I am in this area. So with that, we'll get into the actual the meat of it. What is grit, and why should we be thinking about removing it? Focusing on the why first, in wastewater treatment plants, water resource recovery facilities, there's really two problems that you can see from grit. One of those is that it accumulates in process tanks. So wherever the velocities slow down a bit, the grit can settle out and then occupy volume. That can be an issue in things like digesters or bioreactors, because those processes are all about volume, hydraulic retention time. So if that volume is occupied partially by grit, then you can have impacts on the process. The other issue that grit causes is abrasion. It's oftentimes pretty hard, so that's going to lead to wear of mechanical equipment, and that's going to give you maintenance challenges, leading to more frequent replacements and reliability issues. So what is grit? It should be obvious, right? People think of grit as, well, we know what grit is. It's kind of hard, you know, gritty, sandy stuff. And that's certainly the characterization that we used to use to design our grit removal systems. So if you look on the left-hand side there, we used to think of grit as clean silica sand, dense, relatively small. But that's not so simple. When you look at the photograph on the right-hand side, that's from a grit bin, so you can see it doesn't look really much like the pile of sand on the left. Grit is actually a whole bunch of different things. So we used to design our grit removal systems based on the understanding on the left, things like aerated grit channels, for example. But we'd see that downstream we were still getting grit accumulations. So that understanding really wasn't cutting it. It wasn't nuanced enough to design the systems to remove all of the grit that we wanted to remove. Grit removal is part of a good, part of a good headwork system, just like screening. It's about trying to get those troublesome materials out as early as possible so that you protect everything downstream, and that's becoming more and more important as we get more and more advanced technologies in our treatment systems. So then that leads on to the first thing I'd like everyone to know about grit is that grit is not just grit, it's not clean normally, it's often going to be associated with organics. So when it comes into your plant, your eggshell or whatever else is going to have bacon fat on it, for example. That causes two issues. One is it means it behaves very differently. It's not a nice, clean, dense particle. It's a dense particle covered in lighter material, and therefore it doesn't settle, it doesn't behave in the same way that it would if it was clean. So that affects how we design our grit removal systems. The other consideration is that you want the organics in your treatment plant. That's what it's there for, to remove those organics in primary sedimentation or secondary treatment, and ultimately going into your digesters and your sludge handling system. That's where you want your organics, not in your grit bin. So that means that organic separation from grit is a key aspect of grit removal. Those things go hand in hand. Okay, so switching gears a little bit here, what about grit measurement? And maybe just before I move on, why would you even want to measure grit? There's two real reasons for that. One is if you're looking at a grit removal system, so how well is that performing? And the other is maybe because you want to characterize the grit coming into your treatment plant. How much grit do I have coming in? What sort of grit is it? So if you're going to measure grit, what do you need to do? Firstly, you need to get a representative sample. When we look over here at the computational fluid dynamics graphic, you can see this is showing velocities through a grit system. And you can see those velocities vary. So if you're going to get a representative sample, you need to collect that sample from different areas of the channel, across the width and across the depth, to get a representative sample. How you do that is going to look something like this system down here with a bunch of pumps connected to a bunch of tubes that go into those sample points. And those pumps discharge into conical bottom tanks, allowing the grit sample to settle out into the base of the tank. You normally collect that sample over a period of a good few hours, trying to get a nice quantity of grit, a good representative sample, so those tanks are continuously overflowing. And when you've got to the end of your sample period, you drain off the water, take out the grit sample from the bottom of the tank. Then you get into what you do with it, the sample preparation, you can say, how you actually test it. Broadly speaking, you're going to be using a stack of sieves, graduated sieves. So you put your sample onto the top sieve, the most open sieve, and then the sample is moved through the progressively tighter sieves. How you get that to happen is broadly divided into two different methods. One is called wet sieving, where you wash that sample through the sieves and let it collect onto the different grades of sieve. The other is dry sieving, where you can dry the sample and then do the same thing by shaking the sieves. Normally you will do both of those things. I'll talk a little bit more about this in around standard methods, but broadly speaking, the method that is now becoming common is to firstly wash the sample through wet sieving. Then you can settle the sample in a settling test, and I'll talk about that on the next slide. Then dry the sample that you've collected in each of those sieves and sieve it again under a dry sieving test. Then finally, you can burn the sample to see how much organics you had associated with the sample. Depending on how you do all of those things, you can have a lot of variations. So this is an area of grit measurement which is open to some challenges in terms of consistency and repeatability. So I mentioned that I was going to move on to talk about settling. So you've taken that wet sample, you've wet sieved it, and then the sample that you've collected in each of those sieves, you can settle in an Imhoff cone and measure the settling rate. The finer the particle, the longer it'll take to settle. The point of this test is that you're trying to equate your sample back to sand, so a sand equivalent size. How long would the same piece of sand, the same grain of sand, take to settle if it was that clean silica sand that we were talking about earlier? So it's about trying to relate your raw grit sample back to a standard reference point, clean silica sand. The reason you do that is because your raw sample might settle more slowly, for example, if it's got organics on it, and that's how it's actually going to behave in your grit removal system. So it's about trying to equate what you're seeing back to a standard reference point, but actually what you're seeing is what you're going to really see in reality in your plant. So that leads on to the second thing I'd like everyone to know is that as of today, even though we've got all these different variables in here, there's no commonly agreed single way of doing the test. There's no single test method. Partly because of all those variables, it's not so simple, but also because whatever method we're going to standardize on has to tick a few boxes. It has to be practical, it's got to be possible to be done without taking months or costing a fortune. It's got to be representative. It's got to actually reflect what really is happening in your plant, and it's got to be repeatable. So that's proven pretty challenging to get there, but we are making progress. Arguably, you can look at that in sort of two ways, top down versus bottom up. And starting with the top down, the Water Environment Federation is one organization that's been working towards standardization. WEF has had a GRIT task force working on this for a good few years now. And in 2017, they published guidelines. You see there on the right, GRIT sampling and characterization. Those guidelines don't provide a single method, but they do provide a number of acceptable methods. So like I say, we're making progress. Also looking at this from a bottom-up perspective, the industry is increasingly coming to some kind of a consensus around how the test should be done. That industry being folks like Veolia, who manufacture these systems, and consulting engineers, for example, who are specifying these test methods as part of tender documents, for example. Broadly speaking, that standard method that's becoming a consensus in the industry is the wet sieving, and then the sand equivalent size settling method, and then the dry sieving. And that's the method that Veolia uses whenever we're providing a guarantee on our grit removal systems. So switching gears again a little bit, just to talk a bit about the technology that Veolia offers here. Some folks in Canada might be familiar with the name John Mounier. That was a gentleman who formed a company in 1948 in Montreal, in Quebec, Canada. And that company was ultimately acquired by Veolia. John Mounier is the brand that we use for all of our Headworks products. So we offer a wide range of Headworks equipment, screening, grit removal, and other things related to Headworks under the John Mounier brand. All of our grit chambers are branded Mectan. The first John Mounier Mectan grit chamber was installed in 1981. You can see the photograph there. That was a 270-degree grit chamber design. It's fairly common on the market these days. We're far from the only company that offers that. Today we brand that the Mectan Classic, 270-degree grit chamber. You can see since 1981 we've installed a lot of these grit chambers, mostly in North America. You see the numbers there on the right-hand side. And a lot of those are classics, but also a lot of those are the second generation design that we call the Mectan V, the Mectan Vari-Angle, and I'll talk about that in just a few moments. So staying at the high level, the different products that we offer under the Mectan brand. So on the left here, you see the Mectan Classic, the 270-degree grit chamber. It's a mechanically induced vortex. It has paddles and a motor that drive those paddles to induce the vortex, to spin the flow. Like I say, not unique to Veolia, fairly common design. This is the second generation product, the Mectan V, and as I say, I'll talk about that in the next slide. And then this is the latest product, the biomectan, and I'll be talking about that in the presentation today as well. Looking at the table across the top, these are the product names, the models. They each relate to a different diameter of unit. The Mectan Classic and the Mectan Vari-Angle provide the same capacity for the same diameter of chamber, varying from the smallest here all the way over to the largest over here. The largest 78 million gallons a day, or 295 million liters a day in a single unit. The biomectan actually offers a bit more capacity for a given diameter, but the sizes of the unit stops here because today we're only offering that product in self-standing stainless steel tanks. So these ones over here are offered in concrete as well as in stainless steel down on the lower sizes. So the Mectan V, how does this work? Really, it's like a classic design, only we've introduced the separator disc. This product was launched over 10 years ago, has proven very popular. The reason for the separator disc is to improve grit removal performance. That's the primary reason. How it works is the influent comes in underneath that disc, so your influent channel becomes a tunnel, and the influent then enters underneath the disc. The vortex is spinning around under there, does the grit removal. The grit gets captured in the grit well down here, ultimately, but the flow has to get up through the center of that donut before it can get out into the effluent channel. So that helps to avoid short circuiting. It does a better job of catching that fine grit and avoiding it from flowing out of the system. So that was the primary reason for introducing the separator disc, to improve grit capture. The other thing that separator disc does for you is it gives you some hydraulic separation between the inlet and the outlet. And that allows you to put those two channels or pipes wherever you want around the chamber. 360 degrees of design flexibility in how you configure the inlet and the outlet. That flexibility can allow you to do some good things when it comes to retrofitting aerated grit channels, for example. Here you see a design with 3 mectans retrofitted into a grit channel. That's going to increase performance and capacity in that channel. It can also give you some advantages when it comes to greenfield, new plants, how you lay out your grit removal facility. So this is a fairly large project. It's in Ontario, Canada. 410 megalitres a day is about 108 million gallons a day. These were the next size down from the very largest. So these are 6-meter diameter chambers. And to give you a sense of scale, you can see the installer over here putting the separator disc in. Little guy, maybe you can't see it on your screen, but it gives you a sense of how big these things are. And of course, back to the layout, you can see there's 2 chambers, and this configuration, this sort of 90-degree through the chambers, would not have been possible with a 270-degree chamber. You need the Mectan V to be able to do a layout like this, and it leads to a nice, clean layout, efficient on footprint. So that was the Mectan V. Now the new BioMectan. So we launched the BioMectan in 2018. It was kind of a soft launch in WWTP 2018. The real hard push on it, the big firm launch, if you like, was in 2019 in Chicago, WWTP 2019 there. And this is our booth. You can see the new BioMectan unit on the booth. The objectives for developing this new BioMectan product were partly around doing even better grit removal performance, even better than the Mectan V, especially when we look at the fine grit, but also to really focus on that organics issue that I talked about earlier. Separating organics from grit as a key design objective was really a part of what we were trying to do here with this new product, and doing that inside the chamber. So we launched it, as I say, sort of formally in 2019. We've had a great take-up from the market. We're really pleased about that. A lot of interest. I've given presentations in conferences where people literally cannot get in the room. So that's kind of good that people are interested in this, and certainly the numbers that we're seeing today on the webinar reflecting that as well. So we're very pleased that the interest from the market. We've sent out a lot of proposals for the product, and design engineers are choosing to specify us and to use the BioMectan as the basis of their design now. So it's been taken up very successfully in the market. So how does it work? Just go throughout the way. So looking at this, the flow is coming in over here on the influence side. Comes in underneath that separator disc. So we've kept the separator disc that works so well in the Mectan V. It's not very clear from the graphic, but the flow does come in underneath that separator disc. Then it does a vortex. It's swirling around in the bottom there. And then the flow has to get up and around out of that hole in the donut, so to speak. So this much is exactly just the same as the Mectan V. What's different is the flow then has to get up through this cone. I'm going to call this the dead zone cone, because the flow has to get up and around. So it sort of peels away to the side. And that gives you a dead zone in this area here. So the flow carries on, goes up over the top of this circular weir, and then ultimately out. Because we've got a circular weir in there, that design flexibility that we had from the V is actually even better in the BioMectan. Not only can you put that inlet and outlet wherever you want relative to each other, 360 degrees of flexibility, but you also don't have any concerns about straight lengths or anything like that downstream on the effluent side. So you can do whatever you want with that outlet. So that's the water. What about the grit? So firstly, it's coming around here. It's the centrifugal forces induced by the vortex are causing the grit to be spun to the outside of the chamber, and then it collects on the walls and the base here. This is angled, so the grit drops down into the grit well. We've also got a bit of a lip on that separator disc that avoids that short circuiting still further, keeping the grit in that bottom section. And at this point, you've collected most of the grit, which collects in the bottom and then is extracted on a timer using a grit pump typically. Now, the Mectan V did a great job of removing grit, but still it loses a little bit that gets out from this bottom section, and that's why we've got this dead zone, because some grit can get hung up in there. If it's able to get out from this bottom section, it's either extremely fine or more likely it's covered in organics and therefore is less dense. That's why it's been able to get out with the water, and so we've deliberately created this dead zone where that fine or organics coated grit can get caught up. So let's focus in on that dead zone. And over here, this is the same graphic we were just looking at. What we've done is we've put inductors in that dead zone. See them there on the graphic, and you can see them here in real life. How an inductor works is you pump water into it. So that's a pressurized water feed. And for every 1 part of water you pump in, 4 parts of water get drawn in. That's because the velocity increases, so the pressure decreases, drawing in water from the local area where those grit particles have got caught up. They get fired through this nozzle, high velocity, and then they're fired against the direction of the flow. So you're getting turbulence in this area. That high shearing force and high turbulence cleans the grit, shears the organics off the grit, cleaning the grit, making it dense, getting rid of the organics, frees it up to be dense and to settle. So those organics coated particles are now able to get down into that grit well because they've been cleaned up and got their full density back. So that's the innovation we've brought in with the biomectan. So looking at the broader system, firstly, just to follow the grit path. So the grit collects in the well, is pumped out from time to time using a grit pump. That pump pumps it over to a grit classifier. Hydrocyclone separates off most of the water. The remaining grit with a little bit of water goes into this part of the grit classifier. You have a grit screw in there that lifts it up and drops the grit into the grit bin, which will be placed over here. We offer an optional grit washing system on the classifier. So you can use final effluent for that or potable water. The other water demand in the system is back in the chamber over here. So from time to time, when you're doing your grit extraction, you also need to fluidize the grit that's settled in the grit well. So you need to pump water in there. And we also need the water to run the inductors. So that's a continuous demand. Those water requirements can be satisfied using degritted effluent, so the outlet from the grit chamber. You can pump from there through a centrifugal pump using a Y strainer for those water demands, or you could use final effluent for that as well. If you wanted to have a really simple system, you can delete the grit pump by putting the grit classifier directly onto the bottom of the grit chamber. You should be able to see that on the photograph on the right here, where the grit screw is mounted directly to the bottom of the chamber, avoiding the need for the grit pump. It's available for the smaller systems in the self-standing stainless steel. And there you have grit washing as standard on the grit screw as well. Something to point out here, which is a little different between the Mectan systems versus some other products on the market, is downstream of the grit pump, it goes straight to the grit classifier. Some other grit removal systems can have a vortex product in here, a whole nother sort of unit step, a unit process to separate off the organics from the grit, kind of cup type vortex system that's needed to do the organic separation. With all of the Mectan systems, that's not required because the organics are removed upstream in the grit chamber. So what about performance? When we were developing the biomectan product, we ran a lot of computational fluid dynamics. You can see a graphic over here showing just one of those. That indicated that the biomectan should do a great job of grit removal, even better than the Mectan V. You can see that on the chart there. But that's computational fluid dynamics. So what about reality? To test the real world performance, we ran a demonstration last summer at a treatment plant called Saint-Agathe in Quebec in Canada. And we were taking sewage that had been through the pre-treatment screen. We were pumping that out of the channel. This is the pump we used for that. Pumping it around into the grit chamber through this manifold. Then it comes out through the other manifold on the outlet side, back into the channel. And then periodically we were using this pump down here to do the grit extraction, and that pumped it over to the grit classifier that you can see at the top right. Coming back to these manifolds, this was all about demonstrating the performance of this new product and a little bit of final development work on the product design. So we had a bunch of sample points in each of those manifolds, inlet and outlet. You can see inside of the manifold over here, and those are where those sample points terminate, the objective being to get a representative sample across the area of that manifold on both the inlet and the outlet. We were there for a few weeks on this site. We did a lot of work, ran multiple test runs, each one of those running for a number of hours, between 4 to 8 hours typically, on different days, of course. So we were really trying to test the system under different conditions and as accurately and comprehensively as possible. Some of the analysis work we did on site, you can see the settling cone here in the middle. And some of it we did back in our lab. This is our lab in Montreal in Canada. And some, we even sent some samples off to external labs, accredited labs, to run some further analysis as well. So we collected a lot of data. We're still actually going through some of it today. Far too much to be able to show you on the screen here, but just to give you a sense of some of the data we were collecting. On the top right-hand side here, you can see a particle size distribution. This is from an external lab, and this is for a dry sieving test. So you can see here the curve, and this is millimeters. So below on the table, you can see sand equivalent size analysis, and that was just from one wet sieving run and one sieve from one run. So that gives you a sense of the sort of amount of data we were generating as part of this test. Something that's quite interesting to note is this graph here. So when you look at the red line, this is the result from sand equivalent size analysis. And the blue line is the result from the dry sieving analysis. And that's from the same sample. So what this is showing is that according to dry sieving, the particle sizes are larger than the wet sieving. So thinking back to the purpose for doing this, this is showing that your sample is actually settling more slowly than a dry sieving analysis would indicate. And that's important, of course, because you need to collect that sample, so you need to be designing your system to remove a less dense particle effectively. That's what this result is telling you. The good news is that with all of this work, we concluded that the computational fluid dynamics was correct, and that the performance really is better with the biomectan than it is with the Mectan V. And that was kind of just as well for the team, because we'd spent a lot of time and money getting to this point. So I think for the president of the company, he was kind of pleased to see that outcome. Okay, so looking at the performance guarantees, maybe starting with the bottom here with the biomectan, we guarantee the biomectan to remove 95% of all grit particles down to 75 microns. It's 200 mesh. That is as good or better than any other grit removal system on the market. So there is no grit removal system currently available that will guarantee better removal than the biomectan. The Mectan V is pretty close to that, 95% removal down to 100 microns. I would argue that that's pretty good, especially when you get onto the larger units where, as I said earlier, a single grit chamber for the Mectan V can treat up to 78 million gallons a day or 295 million liters a day. Delivering that performance in a single unit at that flow, to my knowledge, is unbeatable as well. Something that's important to know is that the performance statements are made at peak rated capacity for the unit. So that's 78 million gallons or 295 million liters a day, 100% of the rated capacity over here. What we're looking at on this graph is computational fluid dynamics analysis for the MECTAN-V and different sizes of grit particle. So the dark blue is the finest particle, 100 microns, and then the red at the top, 300 microns. And you can see that as flow rate reduces, removal performance increases. Because units are typically sized for the peak flow at the plant, peak hour flow typically, it's a headworks product, but also the project is likely to stipulate that flow on a future design horizon, maybe 20 years into the future or whatever. What you're going to find is that typically the unit is going to be operating down here somewhere. Not only does it not sort of rain very hard, maybe never meet the peak wet weather flow that the unit was designed for, but because of that design horizon being 20 years out, and because we've oftentimes selected the next size up unit anyway, if you want 70 million gallons a day, we're going to give you a unit for 78 million gallons. That means that the unit is going to be operating down in this range for all of its life, pretty much most of its life, and that's going to give you even better performance than the performance we guarantee. So just getting to the end of the presentation now, getting into some conclusions, some key takeaways. Grit removal is important for treatment plants. I'd say it's only getting more important as our technologies downstream get more sensitive, more advanced. We need to protect them better and better. Grit removal is not just about removing grit, it's also about separating organics. So that's key to any grit removal process to work well, is to separate off those organics. Performance does depend a lot on the method you use. So a performance statement or a performance guarantee is kind of meaningless unless it's tied to a clear test method. And because those methods can be done really quite differently, you can get a very different result depending on the method you use. Veolia offers a range of grit removal systems under the MECTAN brand, and our new BioMECTAN system delivers performance that's as good or better than anything else on the market. So just as I'm handing it back to TJ, I'd like to remind you that Aurelian is on the phone as well for questions. You'll know the difference between us because I'm the one with the English accent and he's the one with the French accent. So with that, I'll pass it back to you, TJ.
Great, thank you so much, Chris, for that presentation. Just to remind everyone, we are able to see your questions if you type them in that chat box to the right. And we have a handful of questions already, but we should be able to get through most of them. But feel free to enter that question in there, and we'll try to get to yours as well. I'm going to start off with a question here that we received is, what is your philosophy? Is it screening first, followed by degritting, or remove grit to protect fine screens from excessive wear? So Chris, can you help us with that question?
Yeah, so maybe to start, I would say it depends on the installation, but I'm going to ask Aurelian to comment on that as the technical expert. He could probably give a more comprehensive answer.
Oh yeah, hello everyone. So usually screenings removal, like fine screens removal, 6 mm, quarter of an inch openings would be required before the grit removal system. Several reasons for that. One of the sensitive item in the grit removal system is the hydrocyclone we use for the concentration after the grit extraction. The apex of this hydrocyclone won't be able to allow large solids that could be captured. So it's always recommended to have a first stage of screening removal ahead of the grit. Then if finer screenings removal is required down to less than 1/8 of an inch, 2 mm, for example, that could occur after the grit removal system.
Okay, a couple questions. I think I could pair them together, but with larger particles in there, say a few centimeters or a few inches large in diameter, if they make it into the system, how do you handle that? Those particles that are a little bit larger in size and not the fines.
So, well, it depends on what type of particles as well, because the heavier particles have could be captured. Obviously, we're talking about rocks in those cases, would be captured by the grit system. There's really a good chance they would be blocked anywhere before that. and if it's lighter particles, they won't be captured by the grid removal system. The vortex separation makes it that lighter particles, like pieces of wood that would float, for example, would go through the system.
And do you utilize a rock trap?
No, it's not mandatory. We have an installation connected directly to a gravity sewer, but for sure, heavier, large particles, even if there's no rock trap, would probably be stuck somewhere. They won't go. Velocities in the channels won't be high enough to bring them to the system most of the time. If it's a pumped flow, we always recommend to have a core screen before the pumps to protect the pumps themselves. So that will protect all other equipment downstream as well.
Okay. Moving to a little bit different question. This is more of a definition question that maybe you could help clarify. It says that in the presentation, you said grit is above 0.21 millimeters. What about particles less than 0.21? Why can't they be also called a grit? Can you comment on that, Chris?
Yeah, I can certainly start on that one. Aurelia might have something to add. That was an old characterization of what is grit. That is not to say that a grit removal system will only remove particles bigger than 0.21 millimeters. It was how grit used to be characterized as particles bigger than 0.21 millimeters. Certainly our grit removal systems will remove, as you saw from the guarantee, particles smaller than that, guaranteed down to 75 microns.
Yeah,
Aurelia,
so now, yeah, we see systems now that would go down to 100 microns, 150 microns, 100 microns, and even 75 microns. Already at 75 microns and smaller than that, we could consider that as silt, no longer grit, really. The issue we can have with grit in any kind of process, as you show, Chris, are abrasion, the accumulation in tanks and all of that. Those fine grit won't act the same way as coarser grit in terms of abrasion in particular, and even in terms of accumulation. So yeah, there's at the moment it's at 75 microns. Yeah, other than that, it would be considered as silt. Really, it's too small.
Okay, thank you. Some questions about maintenance. What does the maintenance look like for this unit? And then specifically, how often do the eductors need to be replaced? And how do you remove those if they do need to be replaced?
So the eductors are protected with a strainer on the recirculation line. And they can be removed from the top of the unit just by lifting the central components of the unit. The eductor's internal diameter, the recirculated water is taken at the outlet of the unit. So all particles that will remain there will be smaller actually than the aperture of the eductor. So we don't foresee any blockage in that matter for the eductors. And in terms of wear by itself, we don't. So that's not considered as a wear item, bottom line. So that shouldn't be removed at any time.
Okay. Going to talk a little bit about the shear process. Does the shear process pump in the opposite direction against the vortex?
Yes.
Yes.
Okay. And then what is the velocity and pressure at the suction and discharge of the pump?
Which pump? It depends on the models and all of that. I don't think we can really provide that information right away like that. It depends on the 4 models. I don't have that in head, but that could be provided with the selection once we do a selection for a specific project.
Okay, and just going down, I have quite a few questions here. I've got a question about if the pump at the bottom could handle stones and pebbles.
So as I said, the recirculation water is taken from the outlet below actually the outlet of the unit. So grit will have been already removed and all of that. So there won't be any large particles that this by. So the pump shown on the photo that was used for the pilot is not the pump that we will use for that we are using for the real units. It was just for the piloting. Depending on the availability, last summer we had to use a pump that we had in stock, but that's not the pump that we will use in the end.
And if the question was relating to the grit pump, that is designed to pump, it's like a mining pump, a trash pump from a mining application. That's where the pump was originally developed for. So it is designed to handle those difficult, larger items like pebbles.
Okay, yeah, if it's the case, the extraction flow is between 200 and 225 gallons per minute. The pressure depends on the total dynamic head of the piping downstream that goes to the hydrocyclone of the grid dewatering screw, so that we will recalculate the exact power requirement of the pump depending on the TDH.
Okay, a question about the performance guarantee. Can you talk about, it says the removal efficiency to remove down to 75 microns is based on what flow? ADF or peak hour?
It's based on the maximum rated flow of the unit, and we always size or make the equipment selection based on the peak hourly flow of the application. So we will select the unit that has the closest rated capacity to the peak hourly flow, and the performance statement is for the maximum flow of the unit. So it's for the peak flow as well, the peak hourly flow of the application, not the average daily flow.
And rewinding a little bit to the MEC10 Classic, can you comment on the performance guarantee for that unit?
So the classic MEC10, so the way to express the performance as a global performance down to a certain particular size is more recent on the market. It's between a bit more than 5 years. The classic MEC10 is still expressed the way it has always been expressed over the years. That means that we have a breakdown of performance based on particle size for ranges of particles. So it goes from above 300 microns, 200 microns to 200 microns, and so on down to 150 microns, I think, or 100 microns, sorry, in that case. So that relates as well on the way it's tested. The global performance of 95 down to a certain particle size, as Chris mentioned, is tested using weight sieving, SES, and equivalent size with the settling velocity, and then dry sieving. The previous statement based on the particle size range is based on dry sieving only. So there's not a direct comparison apart from the particle size, I would say, that are the reference. You can't do a direct comparison between the two ways to express the performance. It's important because it's two different ways to test them. So it's like comparing the same number but in degrees Fahrenheit and in degrees Celsius and saying that one is hotter than the other. It's really two different referential in terms of the way to express the performance.
Okay, we have a question here about expansion. It says, if a plant has an existing MEC10 Classic and wants to add extra capacity or improve the performance of the unit, can they add a BioMEC10 in parallel? Understanding that there might be some change in hydraulics, and use the MEC10 Classic if redundancy is required or during what weather events. Can you comment on that, Aurélien?
All of those options would be possible. I would say that since the BioMEC10 would be is a self-standing installation, you could pump most of the flow into the unit, and the extra maybe wet weather capacity would go back to the classic mectan. As I said, we usually size for the maximum peak flow. So if really the peak flow now exceeds the original capacity of the unit, you definitely need to have another unit. So it's then a choice of either having a new unit that could handle the complete new peak flow, or a portion of it, and have the remaining go back into the existing unit. We can evaluate all those options with the client.
Okay, question about the testing. It says that the grit sampling looks quite involved. Is this a service that Veolia offers? Can you comment on that, Chris?
Yes, a short answer to the question is yes and yes. It is quite involved, and yes, we do offer that service.
And how would what would be the first step in getting engaged with Veolia for this type of service?
Oftentimes, oh, sorry, you go for it already.
Yeah, no, sorry, Chris, but it's our service department handled by Martin Caspar, who's doing those service offers, and so they have they're using the protocol we developed internally and validated, and yeah, they can provide some service offer for grid characterization or grid performance testing.
And if people wanted to follow up on that, they're welcome to contact me. My contact information is on the screen, and then I can direct them to the right people.
Okay, I'm going to go to some more technical questions. It says, which are the efficiencies of COD, BOD, FOG suspended solids of the grit removal equipment? Is that something you're able to comment here today?
Yes, I would say, broadly speaking, most of those parameters are not really going to be affected by the grit removal, things like BOD, for example. In fact, in many ways, the whole objective of the grit removal system is to not affect things like BOD, because that's going to be related to organics, things that have an oxygen demand. Yeah, in many ways, you would want the change in BOD to be zero. TSS perhaps a little bit. The sort of finer, material might be considered TSS, but no. In broad terms, really the purpose of the grit removal system is to remove that harder, denser material, and most of those parameters that were mentioned don't relate to that.
Sort of a combination question here. It says, when will high flow biomethane greater than 203 cubic meters a day be available on the market? And sort of a follow-up too is, are you able to provide the biomethane in a civil-based design?
We don't have any answer to those two questions yet. The development was based on a certain range of capacity, mainly because it was the self-standing type of unit we were looking at. It's not that we don't think about the application on larger concrete tank installation, and therefore for larger flows. But yeah, we don't have any answer yet on that.
All right.
Maybe, sorry, TJ, maybe just to mention that flow that you just mentioned is not correct. It was the largest biomethane has a capacity, and correct me if I'm wrong here, Aurelian, but 50 million liters a day, 50.9, I think is the number, right?
Yeah.
Okay. Another technical question here. Is it talk about adding heat into the process to help with the organic removal? Is that something that you would be encouraged to do?
I don't think so. The main, I see the point, but one of the main goal we had as well in the development of the biomethane is try to keep to avoid using too much resources. That's why there's no longer any mechanical paddles inside of it. It's why as well we recirculate water instead of using wash water coming from the plant. So there was an overall idea of trying to limit the consumption of resources. So an heating system even if I would see really the interest, I don't think it would be viable on a long-term basis in terms of power consumptions and all of that. So no, it has not been looked at.
Now, you talked a lot about the inclusion of this technology within municipal designs and municipal plants, but what about industry? We have a couple questions about industrial applications for this. Can it be used in places like dairy?
That's a tricky question. It's all our experience really is based on municipal grid. So what we can find in municipal sewer wastewater. All the performances are based on a specific gravity of 2.65 for the grid. So it's not a no, but it would require to have a characterization of the particles that the industry wants to remove, whether it's a food and bev or other kind of mining industry, for example. What we see in wastewater is a wide range of different type of materials, but in concentration that will vary. In mining, we could expect to have only most of the time the same kind of particles and with certain size. So it's the bottom line, the unit would work, we think, but we would need to have a clear characterization of what we need to capture, and we would need to size the unit and maybe reinforce the unit or change the hydraulic or change a few items to make sure we can provide an acceptable warranty. So.
Okay, and just to add a little bit to what he mentioned too, is that Veolia really excels at taking a look at these characterizations, and if it's not a particular technology like the Mectan, we also have several other technologies that we could pair together or substitute to make sure that it's the most economic solution for the particular wastewater application. Another question we have is, what is the retention time considered during designing for settling of grit having particle sizes of 100 millimeters?
So for a vortex grit removal system overall, the retention time is way smaller than with an aerated grit chamber, for example. So we're between 30 to 45 seconds of retention within the unit. The separation, it's mainly based on the vortex, not the settling itself. So definitely heavier particles that will have a really fast setting velocity, it will help in addition. But really the CFD we performed took in consideration all the sizes of the particles to make sure that, because it's not only related to the retention time, it's the velocity, the shape of so that's why we did the test after the CFDs. So bottom line, it's a vortex grit chamber based. It's not a settling type like stack tray or something like that. It's not a settling type of design. It's a vortex type. So we are really the vortex helps a lot for the separation and the capture of the particles.
Okay, we have about time for one or two more questions. We have a lot of questions that we're not able to get to in sake of time, but what we're going to do is review those questions, and someone from Veolia will try to get back and answer, at least by email or by phone, to make sure that nothing goes unanswered. A question comes about using this technology for drinking water applications. Can you comment on that, Aurélien?
I would say it's a bit the same answer as for the industry answer. It's really depends on what's the characterization of what we would need to capture and what would be the expected performance, and then we can resimulate and check if the system would have good performance with those type of application.
Okay, and one final question here is, what are the minimum necessary instrumentation required for the entire grit removal system? Can you comment on that?
The minimum what, sorry?
Instrumentation required for the entire grit removal system.
At the moment, we don't really have any instrumentation required. I mean, I
Okay.
don't consider a solenoid valve as an instrumentation, so no, there's no instrumentation required.
All right, well, we have a couple questions left that we weren't able to get to, but as I mentioned, we're going to hand these over to the panelists and make sure that they don't go unanswered. I first want to thank our panelists for joining us here today and sharing their knowledge with this particular technology. And more importantly, I want to thank everyone who spent an hour or so out of the day to join us to learn about this technology. If you have any questions, there's a place in the survey afterwards where you could request to be contacted back by Veolia if you want to talk more about this application. And also just a reminder, if you do take that survey, you'll be entered into that drawing to win an Amazon gift card. So take a few minutes. It takes literally no more than 2 minutes to do, and it will help us out greatly in improving these kind of broadcasts. So at this time, the webinar is concluded. Thank you all for joining us, and have a great and safe day. Take care.